All right, we got a semi-quick hitter, but this one will have results later on in the book, especially once we talk about the new potential formulations. So let's dive on in. So A, we want to show that the electric field is equal to negative, the negative partial derivative of A with respect to T, where A is the magnetic vector potential, and then for Faraday-induced electric fields. Okay. So check this result by taking the divergence and the curl of both sides. Okay, so what we're doing is seeing does this result actually work with Maxwell's equations? And then B, for a spherical shell of radius r carries a uniform surface charge sigma, it spins about a fixed axis at an angular velocity omega t that changes slowly with time. Find the electric field inside and outside the sphere. All right, let's go for it. All right, so from chapter 5, we saw that the magnetic vector potential of r and t is equal to 1/4 pi b r prime t cross r script r hat divided by script r squared d tau prime. Okay, remember prime was source coordinates. Okay, and then r was field coordinates. So we know from this chapter that working with the 𝘰𝘰𝘰𝘰𝘰 law that E was actually the negative partial of the 𝘰𝘰𝘰𝘰𝘰 law of B cross, modified 𝘰𝘰𝘰𝘰𝘰 law of B cross R hat, similar to what A is defined as. So again, this shows very quickly that E is equal to negative partial A partial T. I'll have to write up some more on that because that seems a bit unclear, but that was all defined in the book. Now for the curl and the divergence, let's start with the curl. We know that the curl of E is equal to the curl of the negative partial of A. If we work this through, we take the partial out and we see that the curl of A gives us B. And Faraday's law tells us that the curl of E is equal to negative B over T. So that checks out. We're good to go there. And with this being an induced field, there is no charge to enclose, so the divergence of E does not equal rho over epsilon naught. It equals 0, and we know that the divergence of A equals 0, so we're good to go. All right, so go ahead and now with this for part B, the Coulomb field for the charge distribution is 0 inside and outside. Okay, Q enclosed. What we see here is that Q is equal to 4 pi r squared sigma over little r squared. That was given, but so the sigma has to be applied to the surface, and the surface area of a sphere is 4 pi r squared. Anyways, the 4 pi's cancel. We're left with sigma r squared over epsilon r squared in the r hat direction. And the Faraday-induced field is negative partial of A with respect to T, where A is the given is the quasi-static approximation, which we defined in chapter 5, or equation 5.69. with omega as a function of time, so letting omega dot equal d omega dt, we can just go ahead and take the partial derivative and set these things equal. And then once we do that, we can solve it on through. Pretty easy to deal with there. What we see is that for outside, we have the electric field from the Coulomb, add with the derivative of the vector potential, and you are good to go. That's pretty cool.